I'm presenting today with sort of two hats on, one of these as a scientist in the Urban Energy Systems Lab at EMPA, the other as co-founder and CEO of this EMPA spin-off, Symphony. And I decided I would do because the tools, these two tools, the Ehub tool and the Symphony web app are quite related, that I would cover them both in a single presentation. So the purpose of both of these tools has to do with design optimization of multi-energy systems for buildings, neighborhoods, districts, and cities. So here we're talking about, I mean, this keyword energy hub is something that comes up a lot in all sorts of discussions in the energy sector nowadays. Energy hubs at local scale is one of the main things that we're covering with these tools and how to optimize their design. There is a national scale version of the software currently in development. I'm not going to cover that today. This is something that is being done mostly by my colleagues at EMPA, Martin Rudizuli, who is here today, as well as Robin Mutschler. So if you would like some more information about that, you can also contact them or contact me and I can forward you to them. But today I will cover the local scale, the building to city scale version of the tool, which is the one that I have been working on and developing together with several other people in our lab over the last few years. So first about the Ehub tool. The Ehub tool is based on methodological developments in the projects SCCR PATHFNDR and CCM Secure. So going back to 2016, 2017. The tool itself was developed, started in the SCCR PATHFNDR project, further developed in some of the SCCR joint activities, and as well as validated and developed in various direct contracts with industry partners where we applied the tool to case studies, to neighborhood district level case studies. And the tool was developed, as I said, by various researchers at EMPA over the period 2016-2021. It's still in active development today. And there's still some projects ongoing, PATHFNDR being one of them, where we're further developing certain methodological aspects of the tool. The first version of the tool was originally developed in MATLAB. We reprogrammed it in Python in 2017, and since then have been adding further features, doing validation, etc. And right now, as I said, we have this national scale version in development, as well as an open source version, which is also in development, which both of which I guess will be ready later this year. Currently, the tool is being developed and applied in PATHFNDR, as well as the another suite project which we're involved in, DeCarbCH, also a Horizon 2020 project, and the national scale version is being developed in a project with VSA, which I'm not directly involved in, but my colleagues who I mentioned before can provide some further information about that if you're interested. So talking about the Ehub tool, how it's set up, basically input data, the original version of the tool, and still to some degree today, data is inputted in Excel files where you have technology data, data describing a case study. So technology data is data describing the techno-economic properties of conversion, storage, and thermal network technologies. Case study data is things like energy prices, CO2 intensity of energy demands, things like that. I'll go more into the full parameters later. We're shifting now a bit to using YAML as input format, but it's basically the same types of data. This just shows sort of the structure. This is a bit old, but the structure of the Excel file and what categories of data are included as inputs. So this data is read by what we call a model generator. This is written in Python. Basically what this does, it takes the specification of the problem that is described in these inputs and transforms it into an optimization model which can be solved. And the idea is to solve the optimal design, to identify the optimal design of the energy system based on the specification. This model generator generates a model which is passed to an optimization solver. Nowadays, we typically use Gurobi, but we have also used Cplex and other ones. and then the results come back and are visualized in a visualization module. There are several visualization modules which we've developed over the years. This is one of those things. It's hard to, as you change the structure of the software, it's hard to keep a visualization model up to date. I guess some of you have experience with that as well. But in terms of the focus of our research, both up to now and in the current projects, most of the research focuses on the development of this model generator. One of the main problems being how can we represent the site or energy system that we're looking at with a high degree of fidelity and still be able to identify an optimal solution quickly. Now, in particular, when we get into Symphony, which I'll talk about in a moment, being able to do this quickly is a very important thing because energy planners will not sit around for hours or days waiting for an optimization to complete. So the criteria there are much more stringent. So a lot of the methodological development is focused on what is the right balance between complexity and fidelity of system representation, and how can we push the boundaries there. So now a bit the Symphony web app. In 2020, about a year ago, we founded the EMPA spinoff, Urban Symphony. Symphony, for short, we licensed the Ehub tool from EMPA and further developed it as a web application. First prototype of this was completed in May of last year, and in November we completed version 1, which was released as a commercial product on an annual subscription basis. Typically, users of the software are it's targeted at energy planners, and what I mean by energy planners are engineering offices, number one. This includes companies like you see here, Amstein Walter, Eicher Pauli, as well as energy suppliers like the energy supplier in Zurich, EWZ, Bern, Chur, etc. Now, sorry. Why did we choose to go for a commercial software here? One of so just to frame this, the main challenge that from sort of a energy planner's perspective or a sector perspective that we're dealing with is the energy transformation of the building sector. So there's this challenge in the building sector. How do we decarbonize the energy supply of buildings? For a lot of sites, they have goals like net zero CO2, sometimes negative emissions, positive energy is another one. And the question is, how do you get from where we are now to where you want to be, which is net zero or another goal at some point in the future, whether it's 2030, 2040, 2050. And there's a lot of different pathways that can be followed. Some of them lead to your goals, some of them not. And it's the challenge or task of the energy planner, or at least he plays a large role in it, to figure out what should this pathway look like, which technologies should play a role, and how should they be used. So a typical energy planner, they look at a site like you see here, can be a building, can be a neighborhood or an areal, can be a district, and they try to answer the question, what is the best supply system for this site? In answering that question, they have to answer things like which supply technologies can be used, considering both conventional technologies like gas or wood technologies, as well as newer technologies like power to gas pathways or other ones. They have to consider the potential contribution of different renewable sources of energy at the site. This includes solar energy, groundwater, geothermal energy, river or lake water. Is a big range, and it depends on the characteristics of the site, what the contribution of each may be. Then you have storage technologies, obviously batteries, but also seasonal storages like borehole thermal storages, like hydrogen storages or ice storages that can also be used. And then thermal networks. For a lot of sites, it's a relevant question. Should we, if it's a multi-building site, should we have decentralized supply of, for instance, heating and cooling at the building level, or should we have a centralized plant which supplies energy to the site as a whole? In that case, having a thermal network at the site which distributes energy. And then the question is, what should that thermal network look like? Which buildings should be connected? Where should the centralized plant be located? What temperature level should it be operated at? So these are the sorts of questions that energy planners typically deal with, and they have a lot of experience doing so, but there's several challenges that they are confronting these days. One being ambitious sustainability objectives like net zero CO2, which they have to deal with. Another being new energy technologies for production, storage, and transport. There's new technologies coming on the market every year, and a big question of energy planners is which of these technologies may be useful for a given site or under which conditions, and they don't right now have good methods for answering those questions. And lastly, there's this nice statement, data everywhere, but not a drop of insight, that increasingly the challenge of energy planners is for when trying to design the energy system for a given site is not having enough data, but rather having a lot of data available from different sources, from meters, from public data sources, from the owner of the site, from energy bills, things like that. Being able to bring all of that data together in an efficient way within a given project, such that in a way that helps them to design the optimized energy supply system for that site, that's something that they're really struggling with. So it was focused on these three dimensions of the problem that we decided to go for a commercial version of the tool. And our sort of guide in doing this, how we conceptualize or understand what we're providing to energy planners, is sort of a navigator. So helping them for any site to navigate the optimal path to net zero CO2 or some other sustainability objective for that site. So a bit of the commercial perspective there, what we're aiming at with the Symphony platform. Here you see, before I showed the workflow of the Ehub tool, here we have the comparable workflow for the Symphony web app. Main difference here, this whole workflow is in the web, in the cloud, and the interaction by the user is via the browser. So in the browser, the user creates a project. They can then set up different scenarios for that project, in which they have to define the energy demands at that site, possible energy carriers that should be considered at the site, the properties of imports and exports to the site or from the site. So imports being things like electricity from grid or gas from the network. Possible on-site resources, these renewable sources like groundwater, like solar energy, in some cases wind. Which supply technologies should be considered for installation at the site, storage technologies, thermal networks, etc. And it's possible for, we've set it up such that it's possible to define different scenarios, because for any site, there's often different possible future development trajectories for the site, which need to be considered, and maybe different scenarios in terms of future energy prices. So the idea is that you can quickly set up different scenarios to be able to compare different futures and to identify a sort of robust solution within that space. Once you've set up your scenarios, you can click execute. The execution here is done in the cloud, and then the results come back in the form of a dashboard, and as well you can download the detailed results as an Excel. I will show this, assuming there's a few minutes at the end. I will show how the web app works and what it looks like. So now a bit into the technical stuff. What are the features of the softwares? Ehub tool is a desktop tool. It covers multi-energy optimization, so considering multiple energy streams or vectors within a single optimization. Multi-objective optimization. Most often we consider life cycle costs and CO2 emissions, but there's other objectives that can be considered as well. Multi-stage optimization is something that we've recently implemented, so that you can do planning for projects that are not just for a typical future year, but for optimize a sequence of investments at a given site over several decades. Then optimization of thermal networks and multi-energy grids, daily and seasonal storages, design. In the software, you can do design optimization or an operational optimization. A design optimization being you're selecting what is the optimal set of technologies to be selected for installation at the site and what should be their capacities. Operational optimization being given a fixed set of technologies at the site with certain given capacities, how should they optimally be operated in a typical future year or a given future year. Sensitivity analysis through the definition of different scenarios. And we try our best to develop the software according to a modular structure with an extensible code base, because the idea is that the software is used in different research projects where we're doing different types of studies and doing different methodological extensions. So we want as much as possible to be able to include these different developments into a common code base. And for that, we need a relatively modular structure. What the Symphony web app adds on top of this, number one, cloud optimization. So it takes this whole thing and puts it in the cloud. Number two, built-in databases. So rather than having to input all of the data themselves, the user can draw from certain databases that are built into the tool, or that are data that's provided by third parties via an API. Also, browser-based GUI, so a visual interface that makes it easier to, at each step when you input data, to get feedback on what you've implemented and what the system looks like. Automated model verification. This was this is not something we thought about too much at the beginning, but one of those things that once we got to applying it in real projects, we realized. So I can't count the number of hours applying the Ehub tool in projects in a research context. How, when you get the result back, this model is infeasible, going or unbounded, going and trying to figure out where the hell is where is the source of this problem. And so we, in developing the web app, we really have tried to do extensive verification of the setup of the scenarios before they actually get passed to the optimization software, so that the user, number one, doesn't get these cryptic messages back and doesn't know where the problem lies, but also that every time you click optimize, you get results that will make sense. We're not quite there yet, but we're well on our way. Obviously, results visualization dashboards, that's what I mentioned before, to give the results back in a way that is easily understandable to energy planners. And then there's some things that were, say, when we started off with the development of the software, that were not really on our radar, but once we got to applying it in projects with customers, that we thought, yeah, it's really essential to have these. One example is multi-mode technologies. A good example here is like reversible heat pumps, which have a cooling mode and a heating mode. And we weren't really representing these in an efficient way before, so we added this feature. Also having seasonal constraints on technology operation. So an example here would be like if you have a heat pump connected to a lake water, or say a river water source that has different temperature levels throughout the year, and maybe during certain parts of the year, if you want to use the river water for cooling, but the river water is too warm in the summertime to be able to use directly for cooling, those sorts of constraints need to be accounted for, and so we built in some functions to deal with that. Another one is complex tariff structures. So when you think about electricity tariffs, they're quite complex these days. It's not just about kilowatt hours that you're buying from the energy supplier, but you have to pay the capacity pricing. So for the peak that you buy, and there's day-night tariffs and other time-dependent tariffs. So these are the sorts of things that are also necessary to consider. With regard to licensing, both of these tools are closed source. The Ehub tool is closed source, owned by EMPA, but of course we can share the code with research partners upon agreement in these different projects that we are involved in. The Symphony web app, also closed source, owned or licensed by Symphony, and again we are also as Symphony involved in several research projects and are able to share the code upon agreement there. In terms of spatial and temporal resolution, as I said, we're focusing on building to district or city scale. When we have the lens of energy hubs, we do single hub and multi-hub optimizations. Single hub being where you represent the site as a single node and have all of the supply conversion technologies and demands clustered within that single node. Multi-hub means you have different nodes, maybe each node representing a single building or a single area within the site, and then you have a network or like a thermal network which may connect those different nodes with one another. Temporal resolution is hourly, and sector coverage is flexible, so we cover, as I said, these different energy carriers. Hydrogen is obviously one of these power to gas pathways is one that's increasingly important to be able to cover here. So over the past few years, we've applied these tools to a number of different case studies. First as EMPA, now also as EMPA, but also as Symphony. Some of these have been building scale, like we have an ongoing project with Lidl. Some have been neighborhood scale, like campus in Roche, campus of Roche in Rotkreuz, and others district or city scale. I thought I will take a few minutes at the end to quickly show you we implemented a somewhat simplified version of a case study we did of Baden Nord in the context of the SCCR scenarios and modeling joint activity in the Symphony web app. So I will show you quickly what that looks like in the app. So I'll jump to that in a second. I thought maybe I have a couple more slides just to wrap up a couple points relevant to Pathfinder that I thought I would go through first. First is the future development of the software in the Pathfinder project. So we are, as EMPA, involved in 2 work packages in Pathfinder. One is work package 2, which focuses on district and city scale, and work package 4, which is a P&D project in development. In work package 2, the focus is using the Ehub tool, and we're focusing on the development of enhanced representation of different sources of flexibility, like electric vehicles and vehicle-to-grid technology. One of the interesting problems that we haven't been able to deal with so successfully so far in the tool or so precisely is, let's take the instance of say a campus where you have people who drive their electric cars to the campus and park them there during the day while they're working, and then they leave at night. And potentially there could be business models in which the batteries could be used to provide certain services to the district or to the grid during the time that they're parked there, and optimizing that the utilization of those batteries and understanding how that may interact with the other technologies at the site is one interesting question. Also, demand-side flexibilities, considering demand response automation, IoT, and the flexibility that you may have in the thermal mass of the buildings. And lastly, interactions with ancillary services markets, where if you as a have a technology on a given site that is participating in ancillary services markets, there's certain constraints on the operation of that technology, that component, which have to be accounted for in the optimization. So those are a few of the topics, and then in work package 4, both Symphony and EMPA are involved there, and this is about sort of applying these in the context of a real existing site, and understanding what financial and sustainability value can be realized through optimally utilizing existing flexibility sources, as well as optimizing investments in new flexibility sources. Last slide, linkage to other tools of the Pathfinder project. Honestly, to be determined. I think in the development of the proposal, there were roughly several opportunities that were discussed, but I think there needs to be some more discussion on these topics, in particular in work package 2, to figure out what these links are. Within EMPA, one of the chains of tools that we're working on is we have three tools in our lab. One is a building stock platform, which is building stock data platform based on linked data, which is about integrating different sources of data regarding buildings into basically a big graph database. And then we have CSRP, which is, I saw yesterday, actually, there will be a lunch talk on that in the fall sometime by Christina Orhonig. This data from the building stock platform can be passed to CSRP, and CSRP does simulation of these buildings, whether at the building level, the neighborhood level, the city level, under different scenarios for retrofitting. The energy demand profiles that come out of this can then be passed to the Ehub tool and used for investigating different policy scenarios, technology scenarios, etc. So this is one chain that we're developing, and maybe it's a chain that we can also leverage within the Pathfinder project, but we're not so sure about that yet. So I see now we're at about half an hour. If it's okay, Leah, I would take 5 minutes and give a short demo of the Symphony web app, and then we have 10 more minutes for questions. So here you can see this is after you sign into the Symphony web app. I'm in my web browser. When I sign in, I have an overview of the different projects that I'm working on. As I said, these can be building scale projects, campus level projects, or here, this is the Baden-Nord project that I will show quickly. This project focused on a site which is about a few hundred buildings, and this is a site that is currently heavily industrial in use, but is undergoing a transformation to more commercial and residential use over the coming decades. And this has implications in terms of the energy demand patterns for the site, as well as new requirements in terms of the sustainability of energy supply at the site. And the question was, what is a good strategy for meeting these new requirements in terms of the energy supply of the system for the area? Now, there's a few scenarios here that we developed, and considering groundwater, considering district heating, and I'll just, because it's simple to explain, jump into this base scenario. So here you see a typical energy hub diagram with your import candidates and on-site resources on the left that you have available at the site, energy demands and export candidates on the right, which you have to, so the energy that you have to provide or can provide, and then the technology candidates in the middle, which can play a role in translating the energy available into the energy that you want to supply. Now, what you do in the tool, if you start a new project, this diagram is not here, but what you do is you go through these different steps, adding energy demands. So adding energy demands, adding supply technology, specifying imports and exports, specifying network connections, things like that. As you do that, this diagram gets built up. So if I add a technology, it pops up here, and then the data underlying that is populated in the representation of your site. So just to give you an example, if we go to energy demands, here I could say add new. To add new, I can upload a profile myself. I can select one that I have saved, or I can generate a profile. This is basically generates hourly profiles based on different building types. It's based on data from a project of the Fraunhofer Institute. And then what you get is like a profile like this, which then is fed into your model. Supply technologies, same sort of thing. I can create a custom technology, so add technologies from scratch, conversion technologies or storage technologies, or groups of technologies together, like complete hydrogen pathways. And you can say add from a database. You can select, heat generation technologies, and then the whole idea of having these databases is that it makes it very quick and easy for the user, for an energy planner to assemble a model, a scenario for the site, which they then can optimize. So when you're done with this, then you say, I'm done specifying my scenario. Then you go to execution. You can select which scenarios you want to optimize, your objectives, and the resolution of your Pareto front. Then once you have that, then you can click execute. Execution for a typical problem, I mean, it can take anywhere from a few minutes to a couple hours for a very intensive one. The results come back. You can download them as Excel files. You can view the results in the results dashboard, which is, I think, the most interesting and useful way to get an overview of what's going on here. So here you see for this site of Baden Nord, the Pareto front of optimal solutions, which was identified for the site, cost minimizing solution, CO2 minimizing solution, and some intermediate solutions. And then here you have detailed the breakdown of costs and a lot of data about the technologies that are employed. And I think that the most interesting thing is that you can jump into any one of these individual solutions and look at it in more detail. So here we have, for instance, our cost optimal solution. You see in color here, you see which technologies were installed in the solution. Grayed out are the ones that were not installed. You can see the capacities that they were installed at. And on the right, you have a Sankey diagram, which shows over a year, even each month, what the energy flows, the energy balance in the system looks like. Here, in this case, we have a heavily gas-driven system with a gas CHP and gas boiler. If we look instead at our emissions minimizing solution, we have a different set of technologies, and we have a more wood-based system where we have a lot of the heating provided by wood fed into a wood CHP, a larger installations of PV, also batteries installed, etc. And then you can get detailed information about all of these. Perhaps one of my favorite plots is this one here, where you can look at how all of your technologies are being used. So for instance, if I want to see how my wood CHP is being used, you can see it. These are the full load hours here, and then you have part load is covered there. So that's yeah, that's the basic overview. There's a lot of possibilities with this. Development is of course still ongoing, both of the Ehub tool and the Symphony web app.